So let's take a step back and review some techniques that we can use for problems with ropes and pulleys. This is a very important summary, and you want to study this for your next quiz. First of all, we have to understand the implications when we have ropes and pulleys in a problem. Hopefully they're ideal ropes and pulleys that have no mass, because if we add mass to the situation, that means we're going to have to accelerate that mass as well as any other mass in the system, and we're going to have to apply more force in order to do so to have the same type of acceleration. For pulleys, we need to make sure that the pulleys are frictionless, otherwise they'll bind up our rope and we'll have to take into account how to overcome that friction in the pulley. If we have more than one object connected by a rope, and perhaps the rope is redirected by a pulley into different directions, all we need to do to solve this type of problem is start by drawing a free body diagram for each object, and then if the objects move in unison, if it's a non-elastic rope, then the objects will move in unison and they accelerate at the same rate. And so what we can do is treat the x-axis as a common x-axis for both of the objects. It just bends around corners. That's all you've got to do. Another class of problems is if you were to have two or more ropes tied together, or if you were to have, instead of ropes, maybe solid bars or something like this formatted in this figure, like we saw trusses before on the Tingsboro Bridge. So the trick you can use here to simplify this problem is to take this point where all of the ropes combine, and we'll put a free body diagram right on that point. And now what we can do is we can draw forces acting on that object, and in this case there'll be three forces. And you can map out those forces and apply Newton's laws, decompose your vectors, and see what happens. Pulleys, and this is a block and tackle pulley you see here, are very similar in that we have the spot where all these ropes are converging, and we have something down below. And so the key to solving a problem like this would be to take your free body diagram and use your pulley as your free body diagram. So draw a free body diagram for the pulley off to the side, and what you'll end up with is a force acting downward, and then you'll have four ropes acting upward. And then hopefully you can make some nice assumptions about the ropes, like we talked about above. If we have ropes and pulleys that act the way we would like them to, and you can easily solve those types of problems. So here are some other applications of situations where objects come together and meet up at points. For example, we've got four truss members joining to one point. And once again, what we do is we draw a free body diagram at that one point, and we can analyze that. So here, for example, we have a Pratt truss, and it has 15 structural members. I'm counting each one of these members here and each one of these along the top and the bottom. So what if we wanted to know what the amount of tension or compression was in each one of these members? Of course, that means there are 15 unknowns in this problem, and we'd have to come up with enough information to solve for 15 variables. It sounds challenging, but what we do is the following. First, we draw a free body diagram over each joint, but we're going to assume, for argument's sake, that all the forces are under tension rather than compression. It turns out if that internal force is actually compression rather than tension, that just means our sign is going to be negative. So what we do is we take a look at these several free body diagrams, and of course for each free body diagram we have an equation that sums up the forces in the x direction and the y direction. And we have 9 free body diagrams here, so 9 times 2 equations each gives us 18 equations for only 15 unknowns. And we can actually go through and solve a really big system of equations. And there are simpler ways to do this, and there's ways to cut these problems down. But that's a quick methodology we can use to do this. So for problem number 13, we have a massless frictionless pulley with a weight hanging over each side. We call this an Atwood machine, or a full Atwood machine. These are 2 thought questions we ask in class. And we can answer these easily if we actually come up with a general solution for this situation, which we will do. So for each one, we're going to draw a free body diagram. I'll start with the capital M block. And you'll notice instead of using subscripts, I'm actually using capital versus small letters. So I'm going to assume that M is larger, so the object M will be moving downward. So I'll take that as my preferred direction, as downward plus y is in the downward direction. For the second object, the small m, that one, of course, will accelerate upward. And of course, if these are ideal ropes and ideal pulleys, we have no friction, we have no mass in the pulley, no mass in the rope, we'd expect the tension to remain constant throughout, and we'd expect these objects to move together if the rope's not elastic. So in other words, if object M moves down exactly 1 foot, then the small M box will move exactly up 1 foot. What we're going to do is we're going to use our rule for a rope. We're going to follow the rope. If this side is moving down, that side is moving up, and we're going to call that our plus y-axis. All right, so we'll let the axis follow the direction of the rope. That is the secret to solving these problems. Very simple. So I'll just add in my forces. I've got a gravitational force pulling down on each block, and I've got a tension force pulling up on each block. And of course, we've already stated the assumption that these are ideal pulleys and ideal ropes, and the tension should be constant throughout if there's no binding on the rope or if there's no inertia of the pulley that I have to overcome on one side of the rope or another. And we'll apply the second law for both cases. Substitute in on the left side for each equation the sum of the forces. Be very careful about your signs. On this left block, downward is positive. On the right block, upward is positive. So on the left block, our gravitational pull is a positive. And on the upward tension force, that's actually negative. And that equals our mass of that block times its acceleration. On the right situation, the gravitational force is actually downward in the negative direction, and positive for the tension force equals MAY. We'll do a substitution for gravity equals mass times gravity for both of these. You have to be very careful with your capital and small m's. And what we end up with is two equations and two unknowns. Our unknowns are AY and FT, just as we saw with the half Atwood situation. So what I'll do is I'll solve one of these equations for FT and substitute in the other. And so on the right side, I'm solving that for FT, and I'll substitute that into the left side of my equation. There's my substitution then to make. Make that substitution in parentheses. You will notice, here's the reason why I always do that. There's a negative sign here. You've got to distribute that negative into both of these terms. So if you did not put those parentheses there, chances are you would not do this step properly. So here's the same equation we had on the last page. And the first thing I'll do is I'll distribute the negative sign into my parentheses. And then, because here's my unknown, AY, on the left and right side, I'll collect all of my terms with AY onto the right side. And then I'll factor out my common factor, AY. And now I can just, to solve for AY, just divide both sides by capital M plus little m. And this is my nice simple relationship. So why find a general solution? Well, the general solution allows us to see that our acceleration in the y direction is directly proportional to gravity. And here's our constant of proportionality. We've got a simple ratio of the difference of our masses over the sum of the masses. That allows us to answer some simple questions like this. What happens if the two masses are equal? Well, if the two masses are equal, our two m's up top subtract, and that zeroes out this fraction. And so we got our acceleration is 0, which we'd expect. And that means we're in equilibrium. Remember, we can have two types of equilibrium here, dynamic or static equilibriums, which means either these two objects will be sitting still, like you just see it here, or if I gave one of these objects a little push or a pull, that would mean that these objects would start moving, and they would move at a constant speed after that point in time, assuming there is no friction slowing down our motion. What happens if the big mass is much, much larger than the small mass? Well, we can use dominant term analysis that you learned in pre-calculus. So let's assume, for example, that our big mass is 1,000 grams and our small mass is 10 grams. What we'd end up with is 990 over 1,010. And of course, that's just a little bit under 1, and so we'd have an acceleration to gravity that's about 0.99 or so. What happens if our big mass is exactly twice the value of our small mass? And it's very easy to work out solutions like that just by plugging those numbers in. We can also compare to our half Atwood situation, and you can see the similarity between the two formulas. We have a ratio again. In the bottom we have our sum of our masses, and up on top we have a little bit of difference in these two situations. Now, I'm not recommending that you would ever memorize these general solutions we're coming up with, because we're going to find general solutions for probably 100 different things in this course. All you need to know here to solve this is the techniques that we're using, the 5-step process, and using free body diagrams. And you can come up with this in 5 minutes or less. So let's take a moment to look at some different types of pulleys. And we'll demonstrate this in class as well. So as you can see, we've got two general types of pulleys. Some are fixed. If I were to pull on this rope, the pulley doesn't move up and down at all, but the weight does. Whereas in this case, if I were to pull up on the rope, this pulley would move up as well as the weight. So we've got a fixed pulley versus a movable pulley. These pulleys can also be doubled up in various ways. So you can see these are actually on the same axle, and they're doubled up, which we call coaxial, or they're parallel to each other. So we've got two in a parallel situation. But we can also double them up in this situation, or triple them in tandem, we call this. And the question is, does it make a difference if we use doubled up in parallel or in tandem? And it turns out it's the same thing. So here's an example of a doubled up situation and a tandem situation. And it turns out if you analyze the physics of the situation, the two situations are identical. And as you can see, here are just a few configurations you can come up with single, double, and triple pulleys of various types. And you can imagine there's many more situations that you come up with. And as you'll see, there are some special names for a number of these situations as well that relate to naval history and shipping and things like that. So your job is going to be to apply the principles that we talked about in our general slide that we had before. How do you solve a problem like this? And the key is to focus on the pulley. I can take this pulley right here and I'm going to draw a free body diagram for it. All right, and this is a massless pulley, so our mass is going to be 0. And we can draw the forces on this. We've got a weight pulling down. And actually, I can draw a free body diagram for this weight too. And here's the free body diagram for the weight. So we've got a gravitational force pulling downward. And we've got the tension in this buckle that's connecting it together pulling upward. And let's assume on all these problems that these are going to be in equilibrium, which means these two forces have to be equal opposite. And this same tension force here must be the tension that's pulling down on our pulley. Remember, this FBD is for the pulley. And so that's the same tension, FT, which if, let's say, for example, is 100 pounds. So pardon my sloppy writing here with my mouse. But let's assume if we have 100 pounds in equilibrium on the mass down below, then we would have a 100-pound force acting downward on our pulley. And then on our pulley, what do we have? We have two ropes acting upward. So 1, 2 pulling upward on this. And then I'll let you finish the rest of the problem from there. One question to ask yourself, if we're trying to figure out the tension in the pulley, the force on the ceiling, and the force that we're pulling this with, and we have this in equilibrium, which means either we're pulling with a constant velocity or we're stopped and just holding it still. My question is, does the angle matter here? In question 15, very similar situation, but we have an angle in here. And the question once again, is this any different from our last problem? So now we have a fixed pulley put in a different situation. So once again, my recommendation is you put a free body diagram around each one of these and see what happens. And here's our single movable pulley. Once again, what you're going to do is create a free body diagram around the pulley. On question 18, this is called a gun tackle. We're getting into blocks and tackles now. Are these two situations equivalent? So I can actually draw a free body diagram around this pulley on the left, and I can draw a free body diagram of that pulley. I can also draw a free body diagram over here if I need, and around here if I need, and go ahead and draw those off to the side, draw your forces on them, and see how everything works out. Don't forget your important assumptions that you're making about pulleys and ropes to solve these problems. And lastly, I have what's called a double tackle. You'll notice I have a double pulley up top, double pulley on bottom. These are a tandem version on the right. And so perhaps what you could do is look at this or this as your free body diagram for each situation and see what happens. And some of you may have already known this, but these pulleys are called simple machines. A lever, cavemen, you could imagine, have the lever. A caveman could actually have a little inclined plane. I'm not sure about the nice wagon. A caveman, you could imagine having a wedge and using it. I don't know. These ones I would say are simple for cavemen. Are these three down below really that simple? I don't know, that's just an observation. We've done this situation before already. We haven't looked at it as a simple machine, but we'll talk more about that later. But we'll actually play with this in class to see why this is a simple machine and why this makes it easier for us to get work done.